Uranus remains the solar system's great unknown. Our only close-up data comes from the brief Voyager 2 flyby in 1986. That encounter left two primary questions: whether the planet's core is solid or fluid, and the vertical depth of its 200 meter per second atmospheric zonal winds. To answer these, NASA has designated the Uranus Orbiter and Probe, or UOP, as its highest priority flagship mission for the next decade. Standard optical cameras cannot resolve these mysteries. They are unable to look past the upper cloud decks to see the interior mass distribution. Instead, planetary scientists must use the spacecraft itself as a sensor. By measuring microscopic perturbations in the orbiter's flight path, they can map the gravitational pull of the material hidden beneath the clouds. This mapping relies on Doppler tracking. Ground stations on Earth measure the spacecraft's two-way line-of-sight velocity to detect variations as tiny as 0.01 millimeters per second. Registering those microgravitational variations requires the spacecraft to fly dangerously close to the planet, threading the narrow corridor between the innermost rings and the upper atmosphere. Physical proximity is only half the challenge. The orbiter must maintain an unbroken X-band and K-band radio link with Earth while skimming the troposphere. If the trajectory takes the orbiter behind Uranus relative to Earth, it enters Earth occultation. The planet's bulk physically severs the data link. Any successful flight path must navigate the rings and survive atmospheric drag without losing its radio connection at the moment gravitational sensitivity is highest. A planet's gravity field is comprised of two parts: a static field and a dynamic field. The rigid rotation of the deep interior causes the equator to bulge, creating an even-degree static field. Differential zonal winds, atmospheric bands moving at different speeds, create density perturbations that generate a dynamic field. This comparison illustrates the two primary models for Uranus's atmospheric dynamics. The left panel shows winds restricted to a shallow layer, while the right panel models deep circulation penetrating thousands of kilometers. To determine which model is correct, physicists must decouple the gravity of the interior structure from the gravity of the atmosphere. This requires mapping the gravitational spectrum up to the 8th degree spherical harmonic. This coefficient, J8, is the mathematical threshold required to prove the depth of the winds. J8 is a concrete engineering target. The spacecraft's orbit must be explicitly designed and flown to resolve this coefficient. JPL has developed 3 candidate trajectories for the UOP, all using highly eccentric orbits to conserve fuel. Trajectory 1, the safe route in purple, stays completely outside the rings. It ensures continuous Earth visibility, but its high altitude fails to resolve new harmonics. Trajectory 2, the deep dive in green, drops to 1,000 kilometers, diving between the rings and troposphere. Trajectory 2 has a fatal flaw. The orbiter-Uranus-Earth angle causes the spacecraft to be occulted for 45 minutes at its closest approach. Prioritizing safety yields no new data, but achieving proximity is useless if the radio link is severed during the observation window. Trajectory 3, the optimized polar dive, maintains the 1,000-kilometer altitude but executes a maneuver to shift into a 90-degree polar orbit. This polar shift significantly increases the latitudinal coverage across the planet's surface during the final pericenters. Numerical simulations show how this geometry successfully isolates the J8 coefficient to a 10% relative accuracy. The final obstacle is planetary noise, the piecewise constant accelerations caused by Uranus's internal seismic oscillations. Even under maximum Saturn-like seismic noise, completing 8 polar pericenter passes on Trajectory 3 will mathematically decouple the data. Trajectory 3 is the only viable path to solving the wind depth mystery, balancing proximity, coverage, and telemetry. The mission's second objective shifts from the atmosphere to the interior, determining whether Uranus has a solid or fluid core. Mapping the core requires observing the tidal parameter, how much the planet deforms under the gravitational pull of its moon, Ariel. This planetary flexibility is defined mathematically as the degree 2 love number, or K22. Models dictate that a solid core yields a K22 of approximately 0.28, while a fluid core yields approximately 0.36. Trajectory 3 provides the uniform spread of phase angles relative to Ariel's tidal bulge needed to constrain K22 to a tiny uncertainty of 0.01. The extreme polar orbit required to map the winds is simultaneously the best geometry to probe the deep core. The UOP must simultaneously account for ring mass, atmospheric drag, Earth occultation, and internal seismic noise. Surviving these hazards involves executing 8 polar pericenters while maintaining an unbroken K-band radio lock. The abstract physics of spherical harmonics and thermal wind balance dictate every engineering choice made for the spacecraft's path. Exploring the ice giants proves that in modern planetary science, the mission's success is defined by its orbital geometry. Ultimately, the trajectory itself is the instrument.